Welcome, everybody. So tonight's talk is Compressed Deep Learning Models 10,000 Times with Probabilistic Hash Functions by Anshu, founder and CEO of ThirdAI Corp. So this presentation is on Monday, November 7th. So a little background about our group. We're San Francisco Bay Area ACM. We're founded in 1957. We're a nonprofit focused on promoting the knowledge of modern computing. We want to create community, support networking and hiring. There's a $20 annual membership. Upcoming talks are on our meetup page. And we have about 185 or so past talks on our YouTube channel. So in general, we have 2 monthly meetings, general computing, typically the third Wednesday of the month, and a data science special interest group, typically on the fourth Monday of the month. We offer networking and job hiring announcements. We may work with other societies like IEEE or ValleyML.ai. So we have some upcoming webinar events. I've been working with a book publisher to get a number of speakers, book authors. And so we haven't got the date set yet, but this is likely to be general computing talks over January, February, March. One of them is the VR book, Human-Centered Design for Virtual Reality, talking about a clear understanding of the human side of VR. Without a clear understanding of the human side, VR will always fail. So the VR book bridges the gap by focusing on human-centered design. Another one is talking about the story of engineers, entrepreneurs who laid the groundwork to the foundations of the internet. The third one is weaving fire into form. So one of the book authors is the ACM Sig Kai Lifetime Research Award recipient. So they're going beyond graphical user interfaces or GUIs to touch user interfaces. So this is should be very interesting. An upcoming talk on in data science in the first quarter will be applied effective computing. Effective computing is the intersection of artificial intelligence with social and behavioral science. Studies how human emotions are perceived and expressed. So think of emotional intelligence for your AI. So for tonight's talk, you can chat in Zoom. My name is Greg Mikowski. I'll be the moderator, and I'll read the questions in the chat periodically to the speaker on Zoom. Also, you can chat in the Zoom for technical issues. You can also use chat in Zoom for announcements of jobs or other events. So now let me introduce tonight's speaker. So the topic is talking about increasing in model size generally improves AI, but we want to demonstrate a way to exponentially reduce the compute and memory cost of training and inference with neural nets. The randomized hash tables can be efficient associative memory to reduce the number of multiplications. This challenges assumptions that GPUs are significantly superior to CPUs. We'll show examples with top NLP models on A100 GPU clusters and compare them versus Intel. We can show a result of 50x faster and cheaper inference on one particular use case with embedding models where you can compress it by 10,000 times, going from 100 gig to 10 megabytes, and get an ML-perf benchmark of 0.80 on a terabyte of data. So for some background about Anshu, he's an associate professor in the computer science department at Rice University. He's the founder and CEO of ThirdAI Corp. In 2018, Science News named him one of the top 10 scientists under 40 to watch, a recipient of an NSF Career Award, Best Paper Award at NIPS, MLSys, Most Reproducible Paper Award at Sigmod. So now, if we were live in person, I'd say give a warm round of applause to Anshu, but I'll stop sharing and we can switch over to him.
Thanks, Greg. Thanks everyone for the time, and I'm really excited to be here. It is always a pleasure to discuss with a niche group of people working on real problems and engineering, and talk with them about technology and get feedbacks. So thank you everyone. I am Cmoputation Srivastava, and I'm going to talk about most of what I'm like what Greg mentioned about the results that we are going to show, 10,000x compression, sparsity. I think it all can be linked with AI with hash tables. And this is the kind of stuff I've been working for about like 8-9 years now. And hopefully it will tantalize you with something new in AI. So I will go with a very brief overview of what is going on in the AI world, right? So, I mean, we all have seen, like AI has not been new. It's been like 20, 30 years where people have been talking and developing AI. But recently we have started getting like a remarkable set of accuracies, some accuracies that have really stunned a lot of people. And on this plot, we're just looking at some of the best models, like, that you look for, like GPT-3, NLG, Roberta, all those names. And obviously this is the year. And on a y-axis, we are trying to put the number of parameters. And what has happened is, and this is also being called a name these days, it's called neural scaling law. And essentially, one thing that is consistent across the progress that we have made in AI is that we are making progress with lots of data and very large models. And to understand why this is happening, it's actually, like there was a paper in 2017 by Google that trained about, like 100 billion parameter model in 2017. So it's like, GPT-3 obviously is quite recent. They were talking about large language model, not large language models, but large models for NLP tasks. And there was a statement in their abstract that says that model capacity is critical for absorbing the vast quantities of knowledge, right? So imagine you're training a model on a very big data set, and a data set has a lot of variations. Now, these model needs to understand these variations, and the model cannot be small. That is the kind of argument they were making in that paper. And in the same paper, they said that, well, our goal is to train a trillion parameter model on a trillion word corpus. So it is interesting that in that paper, the data set was about having 100 billion words, and the parameter was approximately 100 billion. And they said that, well, we also have a corpus, a new NLP, text that has a trillion corpus, and we want to train a trillion parameter model on that. And in fact, they fulfilled that in 2021. They trained a trillion parameter model, and there was a paper out there after that. But there is also an information theory argument to understand what is going on and why we need large model. So at the end of the day, no matter whether it's AI or anything, like it's a program. So let's say I want to think about a question answering system. So imagine you type an email and I have an AI that answers that email, right? At the end of the day, I'm giving you a program that takes input an email and outputs an answer, a reply of that email. Basically, it can work with a variety of inputs and produce a variety of output. Information theory says that if this function description is small, it cannot handle multiple inputs and multiple outputs, right? So there is a very well-known theory, a very, very fundamental theory in mathematics that says that, well, if you're producing a variety of outputs for a variety of input, your bit representation of the function cannot be small. Now, if you think about an AI model, no matter what it is, the parameters in the AI model at the end of the day is the bit representation, the size of the program that you're giving to someone. And the size of this program cannot be small if it's handling a very complicated task. And this has been observed throughout. So what we are now seeing is, we can tackle more complex problems, DALI, GPT-3, but the model size has to be big because these are complex tasks. Again, there is some interesting thing going on if you follow what is in the AI world, right? So we started with a whole variety of architectures. There were RNNs, LSTMs, convolutions, a whole variety of architectures. But over a period of time, people have figured out that, well, architectures are not mattering that much, right? I could get the same result that I get with convolutions on images, even with transformers. Right. And even transformers, you can get the same kind of a result with some sort of an MLPs, with MLP mixer and other kind of architecture. In fact, I was responsible for one of, working on Pair Connect, where a simple MLP kind of an architecture can do something as good as attention. So architectures are getting simplified. Like people talk about RNN as LSTMs, and then they realize, well, you can use attention, which has no recurrence in it, but it can still give you state-of-the-art results on some of the complex tasks for even modeling sequences. So one side of the story is, well, you cannot get away with the model size. The model size has to grow with the data set. And the other side as well, even as you grow with larger and larger data set, the architecture may not matter that much. In fact, there are a lot of papers recently these days that talks about, like, simplifying the architecture. Even GPT-3 can be simplified, and there are like thousands of these papers that are hitting arXiv every month, right? In fact, if you look at some of the largest models that are the recommendation models, that in fact, Facebook has a 12 trillion parameter recommendation model. And these recommendation models, obviously, they have a fancy names, DLRM, DSSM, but they are simple, fully connected neural networks. They're not anything complex. So the moral of the story is anything reasonable and big is roughly seem good for most of the tasks, right? I mean, I could do very well on a lot of tasks. Of course, you need enough data. And it's actually smart engineers that are driving the AI revolution rather than any architecture as per se, right? I mean, that's what has that's what is the summary of like what I understand about like what has happened in the past. And I know there is a lot of stuff about, okay, what would be next in AI, right? I mean, people talk about artificial general intelligence, but I think something much simpler has to happen before we even think about AGI to be next, right? So let's look at today's AI, okay? So now, if you go and talk with somebody who's working on recommendation systems, talk with somebody who's working on, let's say, NLP, and talk with somebody that is working on, let's say, tabular data sets, like anomaly detection kind of a scenario. When you talk with them, and of course, if you're from an AI world, you will understand what they are saying if you've done AI. But if you're not from an AI world, you will think that, oh, these guys are from 3 different planets. They talk different data pipelines. They have altogether different kind of models. Like recommendation people will talk a lot about embedding models. NLP will talk a lot about large language models, or like classical and tabular data set. People will probably think about like, trees and XGBoost kind of a scenario. And the data pipeline is different. Engineering is different. The hardware is completely different. And I will say that from an enterprise perspective, this is not scalable, right? So if I have to solve n problems, I basically need n specialized teams. It is extremely slow. And let's say if you're a business leader, you think about, okay, should I incorporate NLP in my business? You go first hire the right set of people who understand NLP. You incorporate the right set of resources, maybe GPUs, specialized infrastructure. Then you give them enough time for the development, and the development will be very unique. It won't look like anything else, non-repeatable process. And then you go into the experimentation phase where the model may or may not see production. And after that, you might realize that, well, maybe NLP does not improve my business matrix so much. So it was all not worth it. And that is unpredictable return of investment. So what I think should happen before we even talk about artificial general intelligence is what we imagine, and this is what we are working at ThirdAI and other places, is about like a universal AI. So how about I can at least combine these words, right? So somebody from recommendation, somebody from NLP, somebody from tabular, they all can use one tool, and it doesn't matter whether your task is tabular, sequential, NLP, whatever we know of. There's one simple API that just you give it a high level description of what the data is, and it does the job for you. And so basically simple pipelines, there is no specialized engineering infrastructure needed. Like, so you can do it on standard CPUs. And for that means is that you can validate hypotheses at the return on investment instant. So what I'm talking about is, imagine, here are some of the laundry list of the problems that I have mentioned: intent classification, recommendation, income prediction, forecasting, query to product, product to product, ad, fraud detection, anomaly detection. What if there is one simple AI, which is all auto-tuned? It naively handles heterogeneous data. Yeah, I mean, we know that you have text, metadata, a whole bunch of things, time series, temporal aspect. We can utilize all that. It does not require any specialized hardware, and it can handle scale, right? And obviously for models to be in production, for example, in anomaly detection or recommendation, which is very real time, we want like very efficient latency. How about, can we imagine something that, and I believe that is at least need to happen before we even go and jump into AGI. And what that means is we can do rapid prototyping and experimentation. I'll come to this, why this is extremely critical to validate hypotheses fast. So, and again, like this is a little bit of what we have been developing, and in fact, we have released it, is what we call the universal deep transformer. So here is a subroutine which is actually doing a time series data set with tabular information. It has categorical, so it's a recommendation: user ID, movie ID, rating, timestamp, and it is keeping track of what movie the user has watched. This is all the AI that you need. And this is actually doing NLP. So this is doing text classification. So you give a text, and a category, and this is trying to do maybe part of speech tagging or categorizing category for intent. So the API looks very much similar. And this I think is probably going to be the next step. No feature engineering or hand holding, and the AI gets better if more data and features are available. So where are we, right? So remember, we started, scale is one important factor. Architectures are, network architectures are simplifying, which is good. But what is the barrier? Why cannot we reach somewhere here? Or what is enabling ThirdAI to do this, and why it is right out of the reach of other people? It's again the scale, right? So we have seen that model architecture doesn't matter as much, right? Large neural networks are the key. And one AI recipe for all seems like you give me lots of data and a very large model, and it seems to get you the best accuracy out of the box, right? If you're working in any production environment, you will see this story repeating again and again. And it's kind of a common knowledge now for practitioners, especially dealing with lots of data, is that you keep increasing the model size and keep feeding the model. And of course, it has to be a neural network. Keep feeding it with a lot of data, and you can see improved accuracy. But why is it in the hands of everyone? Well, the single barrier is the capability to manipulate, play, train, and do inference with very large networks on diverse data set is still not easy. Even with all the all the software development and hardware there, it's not like you can do it within a few minutes and see the results. So I will say that is still not accessible to everyone. And I think training time and cost drives AI innovation, right? So if you go and let's say look at any data science team, the way they work is they first define a problem. So it could be a problem of, okay, I want to categorize customer query into what kind of items they are looking for. And it's basically every AI new application requires first hire a team of PhD, and it's called like a PhD intuition driven search. You then do a whole bunch of experiment, figure out a model, that see if the model is satisfactory enough, then you put it in production, and the production requirements comes and say, oh wait, your model is too expensive, maybe you need something cheaper because I'm not meeting the latency requirement. And again, like efficient inference is all about searching the cheap model with good accuracy. So it's another model search, and essentially if you can validate 100 models 10 times faster than your competitor, then you're going to make a lot of progress, right? So it's all this trial and error loop. And the winner is the one that has the capability to validate the hypotheses faster than others. And you can clearly see who are the current winners in this scenario. Who is coming up with some of the best AI out there is because they have the capability to validate hypotheses which others are even finding hard to imagine.
There was a question that came up. How does using a non-GPU able to handle a large model? Isn't it still necessary to compute all paths through the models? So that's one question.
I will talk about an algorithm. The problem with, was what I was referring from as a GPU was GPUs are not available to everyone, and GPU memories are very limited, right? So when I say we need to handle very large models, these are like some of the Criteo data set. These are 100 gigs models, right? And again, like these are also on public data set. You can find public data set where the model size will be 100 gigs. In fact, we'll talk about one of those. These models won't fit in a GPU, and now you have to go with like distributed GPU. Where do you keep that GPU? How do you experiment with that? I mean, you cannot just write thing that will work. You have to go through a whole bunch of installation, and then how do you integrate this existing foreign software stack into a software stack, maybe that is SQL or something else, and then there are a whole bunch of problems there. So it's not in the hands of everyone. I know people are doing it, but it's not like democratic.
I mean, a simple answer for the audience question was wait for 80% of the presentation and we'll answer that question.
Thanks.
So another question is training time cost for multi-layers or transfer learning that primarily slows AI progress?
I do agree with that, because right now the whole world is thinking about, we'll train this one big AI and use it for all. And people then realize, well, why do I need a model trained on Wikipedia? I want a model trained on my unstructured data rather than Wikipedia to be better. And then now the question is, well, can I really train it? The answer is no. So let's use a suboptimal scenario where something is trained on a different data distribution. So that is also a barrier. Yes. Now let's go over what is the good about like what has happened in AI. So, like the 2021 ACM Turing Award was given for building, linear algebra libraries for to Dr. Dongara for building the linear algebra libraries. And why that was important is because the people have realized over the period of time that all your AI subroutines can be rewritten into a kernels, which are more or less linear algebra operations. And then you can accelerate those operations beyond some, you can get a very non-trivial speed up because of this kind of research. So you can use hardware accelerators, you can use software accelerators and make that work. And that is one of the reasons why we have taken AI this far, because we were able to push the boundaries of validating big models and hypotheses on large data set using some of these works. However, the current practice is not sustainable. And again, I don't have to talk about there are news articles. This is actually, the deep learning's diminishing return. And according to OpenAI, the compute power required for advancing AI is doubling every 3.5 months. And this article that was in IEEE Spectrum that says that to half the error rate, you now can expect to need more than 500 times the computational resources, right? And this is one of the plot that they were showing about how much computation it takes to get the error rates down and its equivalent carbon dioxide emission. The issue is, even with all the parallelism and the linear algebra libraries that are written, we are still dealing with a fundamentally n-cube operation, which is matrix or tensor operations. There are n-cube or expensive ones. So throwing parallelism as it is like burning carbon at 100 times faster rate using parallelism, right? So it's an inefficient algorithm. I will say it's not a sustainable algorithm because it is hungry in terms of flops. It is hungry in terms of compute. And the only solution we have figured out is to burn that at a faster rate using parallelism or some other solution. Again, there's only so much we can push. So here was an article that came out in New York Times that was in 2016, and it was talking about, well, beyond Moore's law scenario where, well, the hardware improvement are kind of hitting a wall. What can we do? And one lesson line from there was, the lesson is that as engineering progress slow, and engineering as in terms of hardware, advances will increasingly come from human creativity. And I want to show you one such example of what we are working on that goes around this wall. All right, so now I'm going to delve a little bit into the technical aspect of what it means to be training large neural networks, right? So we are obviously talking about the state of the art things, which is deep neural networks. So in deep neural networks, what happens is when you show a pattern, let's say in this case, I'm showing an example of a neural network here. There's an image of a cat here. The cat then goes and hits every parameter here and then produces an output. Then you look at the output and say, okay, well, whether it produced the output right or wrong, based on that, you get an error, and then you back propagate and update all the parameters. That is a very high level, simple algorithm of how the deep learning training or the back propagation works. Now, interestingly, to make this illustration more easier, imagine that this is a billion parameter network, and this has been trained on, let's say, over months on certain data set. And now you saw an image of a cat, you did the forward propagation, you realize there is an error. Now the error will actually, so you did a billions of operation to compute the forward pass, you realized an error, and then you came up with a billions of updates. And then at this point of time, you will say, yeah, well, I need specialized hardwares, because even to correct one mistake, I'm requiring 2 billion operations to compute forward, billions of updates, and then updating them. So several billions of operations are there. This is definitely some acceleration that we need. But this is not long known to machine learning people that most of these operations are not useful. So think about this. First of all, if you're using ReLU activation, 50% of these activation will be dropped. So 50% of the activations you are computing. So you take this input, you compute the activation of this guy, and if it's less than 0, you ignore, and you never back propagate back. So 50% computations are discarded. Well, 50% is not big, but then that is there. If you go on and compute the magnitude of the gradients, you will see that 99% of the magnitude, remember, it's a trained network, so it probably has a lot of learning on it. 99% of the parameters will show an update like 0.0001. And only very few thousands of them will have a large update, which means that your mistake on the cat is coming from a very few parameters significantly, and all other parameters are contributing like 0.001. That is what you should adjust them to. But current computations like Adam and all these algorithms will happily go and update that and say, well, I have a GPU, let's do that billions of operation. And guess on the top of it, people will come and say, you know what? Precisions do not matter. Let's quantize. Let's do 2 bits, 3 bits, 4 bits. So essentially, you are ignoring all those updates that are 0.001 or something. So you did all the computations, you did billions of operations, but you only utilized very few, as in few thousands of those gradients, and only those updated get materialized, rest were ignored. In my opinion, that's wasteful. That is what I have been thinking about for the past 6-7 years. There got to be a better way. So here is what we are going to talk about, and this is what we figured out, which we call dynamic sparsity. So again, like sparsity is a very overloaded word. So first of all, if you're thinking, well, yeah, we know pruning can throw away parameters, but again, like coming back to the neural scaling law, if you're throwing away parameters, you're somehow telling me that your model size can be small. And remember our first slides, the model cannot be small, so you cannot really throw away parameters. So static sparsity, as in sparsity in which you throw away parameters, is going to start losing accuracy. And I'll show you one example where you can only get few speed up, right? You can definitely get some speed up by doing sparsity because there is a lot of redundancy in the neural network. But just throwing away few parameters is going to make your, like that's what you can get. If you really want to get like 10x or 100x, that's not what is going to get you there, 100x or beyond. What we are looking for is a dynamic sparsity. So what I'm showing here is on the left is how the dense computation works. On the right, I'm thinking about a dynamic. So every pattern picks up. So imagine this process that I just talked here. What if you can figure out those neurons that will, or those parameters that will have large updates, as in that will even be better than quantization beforehand, and only do those updates. So that will look something like this. You have a pattern, and then there are very few parameters that you're going to update, and rest you're not even going to touch. And that is dynamic sparsity, because every input is selecting a different subset of a network, rather than having a static sparsity where no matter what your input is, it selects the same subset. So that's different. So we are going to look at this dynamic sparsity, and the puzzle that we have here right now. Okay, we get it. There are only, let's say, 1,000 parameters out there, which I should be forward propagating and updating. But how do I figure out what are those thousands? And if I can figure out those 1,000, then I'm done. Because what I'll do is for every pattern, I'll figure out the relevant parameters. They are not going to be billions. They are going to be only few thousand. I'll feed forward, back propagate only on 1,000. I'm only doing 1,000 operations instead of a billion. That's a huge speed up, right? But how do I identify that? Because it's going to be different for every input parameter. Actually, we solve this problem every day in information retrieval, right? So when you type a query on Google, let's say you type ThirdAI or Rice University, how does Google know where to go without comparing your query with billions of other web pages? It has indexed the web. There's data structures, and this is where hash tables are going to come in picture. So given an input, here's the key puzzle that I have. Given an input, can we pick the relevant neurons or parameters without paying the linear cost of computing all the activations? It sounds absurd, because how do we know which ones are large absurd without computing it? But that's where the web search analogy comes in, is how do I know which page Rice University should hit? Well, it's indexed. So we are going to index, we are going to use data structures. In fact, I mean, I can go a little bit into the theory of it. What we have discovered, and what one of the fundamental contribution of my research has been, that there are a very peculiar form of distribution that you can sample from in constant time, right? And it's a theoretical computer science data structure kind of research. If you're interested, I'm going to show you certain papers. But I mean, again, like, so the puzzle here is, if I'm showing you a pattern, how do I know which neurons are going to spike? And this is also, like, I mean, a little bit related to neuroscience, where people know that there is spiking neurons. And the interesting part is the brain does not spend the same amount of energy on spiking neurons versus non-spiking neurons. But the way we do it, like compute all the activation, it's like spending the same amount of energy on all the neurons. So obviously we, like there is some learnings here, but we are going to mimic the brain. We are only going to spend very few amount of, so we are going to spend zero energy on neurons that we don't touch. And we are going to only spend energies on the neurons that will touch in this fashion. And again, like we are going to touch only 1,000 neurons out of 1 billion for every input. And it will selectively pick the right neurons based on this, because of the information retrieval problem. And again, like this is going more into the weeds of it, that, basically, how do we figure out what are big neurons? Well, large neurons solves fundamentally a mathematical problem called maximum inner product search. And what my research has been even during my PhD days is that maximum inner product search is solvable using hash tables. And we could use locality sensitive hashing and create some sort of a what we call like associative memories or scenarios in which, given an input, in roughly few memory lookups, and I'm going to show you how the algorithm looks like, few memory lookups, I can get the relevant parameters. And the question is, obviously, that sounds like too much, right? I mean, I was talking about, okay, here is matrix multiplication and matrix libraries. Now you're telling me data structures. Now you're telling me hash tables, parallelism. I don't even know how that will work. And I will say that, yes, that's a very valid question. How will this practically work? That has been several years of my work. There has been several papers on how we can do this adaptive sampling efficiently, how we can parallelize it, how we can reduce the hashing cost, every aspect of it. And I have worked over it for the past 4 or 5 years. But let's say we got that, right? We got that part. And then I'm going to show you the algorithm. I think there might be a question here in the chat. Oh, okay, sorry, that's not for me. Okay. All right, so let's look at the algorithm. So here is how the algorithm will look like. So what we are going to do is, here is our neural network. We initialize the neural network. So now we just initialize all the parameters. Now what I'm going to do is I'm going to take this hidden layer. And again, like remember, for an input, I want to figure out what is the relevant neuron for that input, right? So I'm going to throw this into hash tables. So in this hash table, I have a key and a value, and the value is the ID of the neurons, so 4, 3, and maybe this bucket has 1, 2, 5. And again, this hash is locality sensitive, something like information retrieval. So when you say Rice University, it goes to a bucket where the page corresponding to Rice University is located. And this is the kind of data structure we are using. And again, like I'm not going to do the details of what that data structure is, but there is a science around it. There is a way to do maximum inner product search. Same thing, I'm going to do this for this layer. So what I did was I initialized the neural network, and then for every neuron, and remember, neuron is nothing but a weight vector, right? It's just a weight associated with this. And so it's a vector. And all I'm doing is I'm reorganizing vectors in memory. So these are like memory location, key value. And based on the hash or what is the value of these parameters, it will come. You can also think of it as a soft clustering. Now, let's say I got an input. Now my input is going to figure out what are the relevant neurons. So you're going to compute some sort of a hash on the input, some sort of a fingerprint of an input. And let's say that fingerprint turns out to be 3. Then you will say, okay, what is that bucket number 3? And you will go to this memory location, and then you will find neurons 1, 2, and 5. And those are the only neurons you're going to pick. So you are not going to use 3 and 4 neurons at all. Remember, you don't touch 3 and 4. You don't spend any cycles on them. Now you compute the activation of 1, 2, and 5, and this is obviously 0 by default. Now you have another vector, and this becomes an input vector for the next layer. So now you're going to hash this and figure out what are the next set of the neurons that you're going to pick.
So just for similarity, it's what the activation size. So the output activation of nodes, in blue nodes 1, 2, and 5 are similar in magnitude. They're like large positive. And that's how you're grouping them together in the LSH, the locally similar hatch.
Yep. Yes. And then I get a vector, which is the value of this activation, 0, 0, and the value of this activation. That's the vector that goes into another layer. And now I'm trying to figure out which neuron should fire on this pattern. So that goes to the next table. But as you can see, just by hash computation and memory probe, I have a sparsity pattern of the neural network. Now, what I will do is I will feed forward only on these neurons, back propagate, and this is my sparse network that I'm going to feed forward and back propagate. So I'm only going to update these parameters, and the parameters that are not here will not be touched. Now, once I have updated the parameters, I have to update these neurons' location in the hash table. So remember, maybe the hash table previously was this, and let's say after, because these weights are now changed, so the neurons need to move if they have changed significantly, and maybe they moved, and that is what is going to get updated in the hash tables. But all the operation here is of the order of active neurons, the neurons that I need, including updating the hash tables, and the parameters that I don't touch are not the part of the computation. So if you imagine this network to be a billion parameter network, and these are probably a few thousand parameters, all these operations are of the order of few thousand rather than a million or a billion. Now, here is another bonus. Let's say if I'm training the data, and again, like remember, gradient descent is not a parallel operation, right? Because if I'm doing a dense gradient descent, let's say I figure out my image of a cat and I did backpropagation on cat, and let's say there is an image of a bear and I did backpropagation on that image. Ideally, this should be done in parallel, because whatever network change is going to affect the prediction of this guy. But somehow, if it so happens that the cat and the bear, they activate a whole different set of parameters, then I can update them in parallel, because whatever update are happening here does not affect this guy. That is what sparsity buys it. And it's a well-known fact. It's called the theory of Hawkwild, that you can actually parallelize gradient descent, and it's gradient descent, and it's data parallel gradient descent. Now, this is the algorithm that we have implemented in our board engine. So this is, we created, again, like we had a prototype, we wrote a paper about it, but then we realized that we really have to commoditize this and to give it to everyone, in the hands of everyone. We really have to build the software stack. So we build the software stack in C++. It's written in, like primitive C++, and then it has exposed bindings in Python, so that you can use it just like any other libraries like TensorFlow or other thing. It works on laptops, ARM, on any x86 processor, CPUs only. And most of the choice, like we also figured out a way to make it easy to use, so everything is auto-tuned in it. In fact, we can train tens of billions of parameter models on a desktop. Here are some of the results. So we took like the Kaggle recommendation model data set. This is Amazon 670 recommendation model. What we are looking here, the gray lines, and these are different processors. So this is Apple M1, this is Intel Xeon, this is AMD EPIC, this is NVIDIA A100. So this uses, NVIDIA does not use our algorithm, it uses CUDA. This is like the most optimized libraries on these processors. So this is Intel MKLDNN. This is, whatever AMD, I think it's TensorFlow. This is also TensorFlow for, like optimized for M1. And this blue line is this bolt package that we wrote in C++. And this is a 200 million parameter model, neural networks, and this is time per epoch, right? And obviously you can see the plot here. This is the time and the accuracy climb. And bold, this is on Intel CPU versus even A100 GPU. Obviously, if you take TensorFlow on CPU, it's worse than GPU, which is what you will think, because these guys are doing dense computation. This is like adaptive sparsity. And things become even more interesting when you're training something like 1.6 billion parameter model. So this is AMD EPIC with about it's very easy to get 200 gig RAM desktop, right? So model parallelism is never a problem. But for GPU, 1.6 billion parameter model with a large batch size, you need 4 NVIDIA A100, and still the time you can beat it with a single CPU. And these are cheap processors. It's not like even an expensive one.
You say with a large batch size, why not just shrink the batch size to something smaller? You don't have to use a batch size of 1,000. You can use a batch size of 20.
So we tried all that. I think it might fit in 2x if you go very stingy on the batch size, but then the accuracy and it's also the question of like too low batch size also hurt the accuracy, but it also hurts the speed, right? This is with this is enough parallelism to use that batch size. So yeah, I mean, but then the thing is, you don't have to worry about, like, it will definitely not fit one NVIDIA A100, but you can even be faster with like the most favorable scenario there, with a sparsity based acceleration. And again, this is all on CPU, C++. You don't even have to change your software stack, right? You can use the current software stack. Don't worry about a foreign driver that you don't understand, and it fits in well. Now, one interesting thing to note here is that when we do this, we do the forward pass and the backward pass both with sparsity. So inference is sparse by design, right? So here is what we do is our inference is also faster, right? So we compare it with OpenVINO, TensorFlow. Obviously, you can accelerate it on GPU with batching. And you can see that the gains here are only 1.4x. In some cases, like for some models, it can be good, like 18x. But correspondingly, we have an order of magnitude better gains. And this gain is for free because it comes for free. Like both training and inference are fast in this engine. And again, this is on a CPU, the same CPU as you can run the OpenVINO. So why it matters, right? So existing package like PyTorch, TensorFlow are great to quickly test a certain variety of model for accuracy. And then when I say a certain variety, the model has to fit on GPU, it has to be in certain size, and it has to be of certain form, right? How many of you have, like, if you want to train a really wide neural network, you cannot train on TensorFlow on GPUs. You cannot, right? Think about, like, if your data has 1 million dimension, have you ever seen that? That will never work, right? So there are a lot of data sets on UCI on which you cannot train neural networks, even with your favorite tools. So it's great for quick prototyping and testing a set of models for accuracy on a particular task. However, they cannot help with resource quality trade-off. They cannot explore the landscape of sparsity. So for example, they cannot help you with energy efficiency, cost efficiency. If you're asking a question, well, given a model, what is the most cost or energy efficient way to deploy it? I don't think existing package will give you that. Can I accelerate to really large model and large data set easily? The answer is no. You have to figure out, you have to come up with a new hardware infrastructure and then build the best AI for that hardware infrastructure. And there is no correct answer without deploying that hardware. And again, like now we talk about this, once the hardware itself become an issue, the deployment and the prototypes are not even easy, even in that case. And one is first even developing a prototype, and then the next stage is going to production. Here is a use case that we are actually on a real customer environment. So this is basically running a real-time query recommendation system. So when you type something like backyard sitting, the complaint is that, well, I don't get outdoor chair because there's no NLP in the model. So obviously you can go to Hugging Face, download your favorite Roberta or other models. You will love the accuracy, but they will take your latency to something like 200 milliseconds. Now, in the production environment, many people are constrained with something like 10 or 20 millisecond latency. With the Bolt engine, we are actually training even bigger parameter models than the Roberta. We can beat the state-of-the-art accuracy like anything, and we give a latency of 1 millisecond because of the sparse inference. And this is a real use case, so you can drive relevance with this software. Now, here is something quite interesting. So when we talk about this algorithm, right, this was sparsity, but then we can use sparsity as a norm. So I can give you something, and 0% sparsity means no computation. 100% sparsity means dense computation. And I can give you this whole spectrum, and you can ask a question, okay, let's say if my budget is 5% sparsity, what is the best accuracy I can get? If my budget is 10% computation and carbon footprint, what is the accuracy can I get? And it turns out that in many cases, you will see that 5% sparsity is good enough. Now, if you're worried why PyTorch and TensorFlow does not give you this, there's something called dropouts, and you can, try this dumb experiment with PyTorch and TensorFlow. Go tell them, I want to do 1% dropout. Don't worry about the accuracy. 1% dropout means you are not doing 99% of the computation. you will see that it will cost you the same amount of time, the same amount of energy, and same compute to even train this model that has only 1% of computation by design. Whereas when we say 1%, you can actually see that 1% in training, inference time, and carbon footprint. And on the side, what we are showing here is Roberta that requires 267 carbon footprint equivalent, which is like burning several big light bulbs. And Bold, to reach the same accuracy, you can actually deploy it on a different kind of a CPU with different sparsity, and you can see that it's more or less like an energy of an LED, right? You can train the same model, and it's training, as actually training and fine tuning. So, that is the something that is incredible for me, that it can give you the whole spectrum. All right, if there are any questions, then I want to talk about the compression stuff, the 10,000x compression that we talked about. So there is a question, do the inputs in a batch all have to be similar so they activate the same network subset? How would you group them? So that's a great question, Eric. Right now, we do not group them. We just, we assume that right now what we do is we do data parallel. So every data in the input is in a different thread. And if they are similar, then they will kind of activate same network subset. Then we might have to wait for some synchronization, but there is a way to even avoid that. We have figured that out, but we don't have to worry about this, at least for now in the package.
A question is, why does your system fit better on Intel versus NVIDIA? Is it because the NVIDIA memory is smaller and you make use of memory is more important, or are there things in the AVX that vector instructions that you make use of? Or
so right now we don't make use of a lot of vector instructions, because remember, our access pattern is also very randomized. Remember, it's a hash table and it's a random hash table. We have not done any implementation on A100 right now. So, I mean, because obviously we don't need that much parallelism, but it's an interesting question. If we have that, what can we do? We haven't done that. Right now, the implementation available is only for CPUs, right? That is what the Bold package is only available for CPUs. It's not available for GPUs right now.
Just focused on that because that's the major market.
Yeah, I mean, right now, first of all, like, we can target a lot of people with that. And I think that already shows the value. Maybe in future, what we can do is we can say that, okay, now we have an acceleration of all the GPUs. Let's make it even more appealing. And we will see, but it is an exercise to go over it, because GPUs have small memories. And then you have to figure out how to coalesce your memory access to actually make use of that massive parallelism. Right now, we have a lot of random access. So it's random memory, we have to be a little careful with the cache thrashing and stuff, right? So we have done all that optimization, but if you do a very basic optimization, you already see a very exciting result. So that is what the current focus is. Yeah.
Okay, thank you.
Oh, there is a question in Q&A. How will this address systems that require continuous learning? So again, like, this is also one thing to understand is, once I make training, how about, let's say, if I tell you training will never be a problem in terms of cost or time, then continuous learning, the best way, by the way, continuous learning is still in, there are a lot of papers written about it, but one thing that short works is retrain everything, right? And in fact, I have seen many companies do that, because to get the best accuracy, the best thing you can do is take your training data, append the new data, add it, and retrain. And what we are seeing is what if the training cost is none? Obviously, there are smarter ways to do continuous training. You can do it, and you will still reap benefits. But if there is no cost associated with training and it's fast, you can as well retrain. So it's actually very appealing for continuous training or continuous learning perspective. Thanks for that question. All right. So let's talk about a compression. So we started with, we need large models. And again, like, the question always is how large? And I think we
I was going to say there's a few other questions in the chat. So let's see.
Okay.
Can you comment on collisions of the hash functions, or what are the hash functions? Is it task specific?
So yeah, so hash collisions. So these are like locality sensitive hash functions. Again, these are not like your cryptographic or universal hash function with separate things. These hash function recognize that if two inputs are similar, they will have kind of collision with high probability. So hash collision determines that you're kind of looking at similar parts of the input, or the input that should go to the same set of parameters, right? These hash functions are locality sensitive and they are not task specific. You can have one or two kind of a hash function for a variety of tasks. In fact, in our bold implementation, we just use two kind of hash function, and that is almost the works throughout our scenarios. We can do time series forecasting, we can do Q&A, we can do NLP, we can do recommendation with one or two hash functions. Right now, we are not working on vision and speech cases, but other than that, we have not seen need for any other hash functions.
Okay. Another question is there a comparison of this work with neural magic work?
So neural magic falls in the bucket of pruning and quantization. We do something very different. So our technology is completely different. Now let me add a few things here. See, there are two lines of work, right? And this is a great question, by the way, because that also gives us a scenario of why they are different, right? So one line of work is you train a model, and now you want to say that, well, I'm not going to let you touch the training process. Now, why don't you go and figure out what is the best way to deploy it? And then you are left with no other options but to maybe do pruning, quantization, because you're not seeing the training process. And what we believe is that there is only so much you can do, right? You will quickly start losing accuracy. Now, if you look at our process, even during the training, the inference is sparse, and that determines the training. So the training process is aware of what the inference is going to be. See, the inference is extremely sparse. And by the way, we are 99.9% sparse on every input. But it's different kind of a sparsity. But when you are training, the training knows. So the error made during training could be the error of the model parameters, could be error of the approximation. But the training process knows what the error is, and it constantly keeps training. So we can actually show you 100, 200x. Like, for example, in this use case, if you think about it, 200 plus millisecond, and we are giving 1 millisecond. And this is like actually something like a Roberta model. So it's a different set of technology. The messaging may seem like similar, that we also have sparsity. We also do things on CPUs, but that's, the technology is different, right? The idea is different. The technology is different. We use hash table based sparsity for training and inference. And again, like inference is not very different. Our neural network itself, the feed forward itself is sparse and the back propagation is sparse. So when you deploy it for inference, you get something. We don't do any pruning or quantization right now.
Okay. Another question is, let's see. Thank you for explaining. Makes sense on the neural magic comparison. Let's see, on the Q&A, there was from YouTube. It says, this is really exciting. Is it only recommended for client-side processing or using for scaled cloud applications?
It is recommended for both, right? Client-side, so right now we are deploying both on-prem and on cloud, and we do both. So again, like this is a new software stack. It is written in C++ from scratch, and literally at this point of time we can deploy it anywhere, because we are not dependent on TensorFlow, we are not dependent on PyTorch. This stuff is not dependent on any of those, so it doesn't come with any of the burden. It's bare metal C++ code. Okay,
you're all caught up on all the questions. Thank you.
Thanks. I think there was one more that says, was there any drop in generalization, by Nitin? So Nitin, that's an excellent question, because it may feel like, oh, wait a sec, you're doing some sort of an approximation. Could there be drop in generalization? And generally, I avoid this question. Why? Because we generally see gained generalization. Why? Because of dropouts, right? So, I mean, I don't know, there is a connection between dropouts and regularization and how much you know about it. But the way we are doing, our networks don't overfit because of this randomly picking set of parameters for every input. And we actually see even improved performance. So if you do the dense computation, you get to certain accuracy, and often we see even slightly better than that accuracy. So, again, like I don't want to go deep into why or what it is, because people don't understand generalization in neural networks very well. But I will leave it at that. These are dropouts. So these sometimes even give you better accuracies.
Sure. A new question came up in the Q&A. Are you considering building custom hardware to handle the hash function? Seems like perfect for edge deployment.
I think this is a great question. So right now, again, it depends on the use cases. Right now, we can work on any CPU. So even on edge deployment, and I think talking about like edge deployment, I'm going to show you something that we can even deploy some of the most heavyweight ML perf model even on edge. But right now, I think CPUs can already go very far. So we want to see how far we can even push the existing CPU. Now, if we come across a use case, well, you know what, even this is not enough, then that's a great future work to think about. Okay, if this is even not enough, but this is what I think is a sustainable AI, then it makes sense to build a hardware for the sustainable AI because it's cheap and energy efficient. Thanks for that question. Is the hash function predefined or learned? That's a great question, Lonnie. Right now, in several applications, we do predefined hash functions, but for certain efficient inference, we can also learn it. It can be part of the learning process too. That's a great question, Lonnie. All right, let's quickly look at how we can compress. So we started with like we need large models, but we never went on how large, right? Should it be 178 billion parameter, maybe 10 billion, maybe 1 billion? And it turns out that there is a lot of redundancy there too, and we can compress something incredibly more than what we think we are possible. So this is based on two publications. One is going to appear in Neurons this year, and the other one that appeared in MLSys in August. So the focus and what we showed was the focus was this MLPerf Criteo benchmark, which is the largest public benchmark for HPC model. And when we looked at this model actually, like it's a click-through prediction. So you're given a dense set of feature and a bunch of categories, and you're asked whether there is a click or not. And people deploy a recommendation model. Now, what is interesting is the sparse features are very high dimensional, right? These are like about 1 million dimensions, right? So there are millions of possible sparse feature, like could be some attribute of what was shown and to click or not. And what people do is, instead of doing the full matrix multiplication, by the way, it's equivalent to that, they do an embedding table lookup. So for every feature component, so if there are 1 million features, there is this table will have 1 million vectors, each of, let's say, some 1,000 dimension or something. And then what you do is you do an MLP here, you do a lookup, then you combine those embeddings, then you do all the interaction feature, which is like just running these through another neural networks, and then you do a final layer of a neural network for prediction. Now, it is well known, and this is again coming from MLPerf benchmarks. So this is like the MLPerf size is the DLRM. The multi-layer perceptrons are only 10 megabytes. But the embedding tables are about 400 gigabytes. And in fact, Facebook has a 100 terabyte embedding model. This was a paper that published this year. The terabyte benchmark, which was the MLPerf cares about, is a 400 gigabytes. So this is actually 400 gigabytes of parameters here and about 10 megabytes of parameters here. So most of the parameters are here. And what happens is that this is incredibly a memory latency bottleneck. So this is memory bandwidth dominated. And in fact, this is the bottleneck of the computations. So why are embedding tables large, right? Where are those 400 gig coming from, right? And again, so these are basically, so let's say I have input tokens, which could be something like NLP. So I have a word cool, and there are probably about 1 million words. Cool is word number 512. So 512 will have a vector, and this is an embedding corresponding to this word. So this is an embedding table. Now, even if there are 10,000 words, you multiply that by like this hundreds of hidden unit dimension, you can still see that it's not difficult to just have a very large embedding tables, right? And the categorical data, usually words, colors, pages, they have a lot of categories, and high hundreds to millions of billions of, you can have a lot of tokens. And that's one of the reasons why this Facebook model that has 100 terabyte of memory just to store the embedding tables. So just let's review at what have people done. And obviously, we are not the first one trying to see about, okay, can we compress this model? Because obviously it's a big model, so everybody wants to compress this. There has been a flurry of work starting 2018 where people can do 2x, 4x, and suddenly people realize that you can even go in the realm of 10x or 100x with some sort of a low rank kind of an idea. And I'm going to show you some of our work, which is 10,000x. So what is this 10,000x? And before we even go that, Let's think about again, like, I mean, so the MLSys work was talking about 1000x and the new work, Neurons talks about 10,000x. So let's look at 1000x compression. What is 1000x compression going to give you? Remember, if I'm having this kind of a model, which is 400 gigs, and this is ML per terabyte, the largest ML per benchmark. If I do 100x compression, it becomes 400 megabyte. That will fit anywhere. I never have to worry about model parallel training, right? The inference time will be fast by design because the memory latency has gone. I will have faster refresh cycle and we can accelerate recommendation. We can even deploy. If I can take a 400 gigs model and get you into 40 MB, I can deploy it on your cell phones. So here is the idea of how we are going to compress it. So let's say this is how, like, I'm just trying to give you a visual picture. These are my embedding tables. So this could be an embedding for a word, embedding for a category, and I have a bunch of them. And this is like what is occupying most of the memory. What I'm going to do is I'm going to replace this whole embedding table by a fixed size array. And this array size is anything that you can choose, right? And obviously, if you choose it too small, you will hurt your accuracy. If you choose it too big, then memory is an issue. So, but you can literally choose it as big as you want. And in this case, we are going to choose it like 10 MB or 100 MB. So this is all the memory that I will use. This is only for a conceptual purposes. This is the memory that will be never materialized. But imagine a model has this as a memory, right? And then it's accessing and doing computations on these memories. Now we are going to mimic this computation by only using this memory, and this is only there to show conceptually. It's never physically materialized. So let's look at one embedding table. Let's say a model comes and say, I want to access this memory. Give me this vector. And I'm just giving an example. We call this the row array. So what we are going to do is we are going to say, okay, I'm going to give you this vector. Let's, for the time being, divide that vector in 2. And 2 is just illustration. In practice, we divide in 5, 10, whatever that number is. But just to give you an illustration of 2, what I'm going to do is I'm going to divide this vector into 2 parts, part 1 and part 2. And the token is x. So I now have x1 and x2. What I'm going to do is I'm going to hash randomly x1 into this row array and hash randomly x2 in the row array. That's the parameter corresponding to the. So this will be the value. This will be the value. And it's all coming from this array. So if you see this, obviously you will say, okay, you are taking a very big memory and replacing it by a small memory. There are going to be a lot of collisions. There is a lot of parameter sharing. Yes. In fact, we call it a random parameter sharing scheme. So this parameter, for example, is used by hundreds of different embeddings at different places. But that's what is the nice thing about learning and the theory that we have. In fact, it's also provable. You can provably show that this will work. So what you're going to do is you're going to take this whole embedding table, which is 400 gigs to 100 MB or 10 MB, and we call it row array. And that is how it will work. So as you can see, whenever somebody asks me, what is this embedding? I'm going to give those 2 values. And whenever somebody asks to update, I'm going to update the corresponding in this row array. And that is pretty much more or less what the idea is. And what we did was we ran this model. Obviously, one thing is you need to train it slightly more. So you have to train it more epochs than usual. So MLPerf cares about this accuracy. So this is MLPerf criteria benchmarks. It's asked you whether you read 8025 accuracy. And we are using row 1, 8, 30. These are actually, what is the size of this? What is the size of this? Is it 1? Is it 8? Is it 128? That is what we call the row 1, row 8, 32, 128. And as you can see, the larger this is, it will result in better caching. Now here is the original model, which is 100 gigs. And all these rows are 100 MB. 1 is the chunk size 1, 2 is chunk size 2, 8, and so on and so forth. And as you can see, we are processing samples per second, goes up as I increase this. And obviously it's even better than the original one. And this is the latency of feed forward pass. So this is inference latency. So we can get about 3x faster inference latency just by doing this. Can we achieve this accuracy? The answer is yes. This AUC was reached in 1.89 epochs. Now that is one caveat here, that the original model reached that accuracy just in 1 epoch. We need a slightly more number of epochs, but wait a second, this is 1000x compressed model. It's totally worth it. So we call it block-based hashing. It's cache efficient by design, theoretically superior. And I think it's a generic solution to parameter explosion in a recommendation model. It can train even on a single GPU, quality maintained, faster inference, faster training. All right, I think that's pretty much it. And I want to quickly wrap up now. This is the most exciting time to revisit algorithms and data structures. We have been riding on matrix multiplication and hardware for a while, but it's slightly hard to keep it up. To meet exponential demand, we need to go to the drawing board. So this is what I teach in the class, right? I mean, I say that, well, like, let's say you are in a system, and somebody comes and say, hey, I want to make the system 1.5x efficient. All you have to do is to keep all the fundamentals intact, roll your sleeves, and do every inch out of your textbook to make everything efficient. You will get 1.5x, 2x, or even 3x. But if somebody comes to you and say, you know what, 1.5 or 2x is not going to cut it. We need 10x, 100x, 1000x. You cannot keep the fundamentals of the system the same. You have to revisit. You have to go to the drawing board. And that is what we have done. If I have shown you an algorithm, which is actually an algorithm resulting after going from the drawing board, coming out, and now we are even applying it and seeing, remarkable results. Hopefully I have convinced that dynamic sparsity is a very promising approach. Current package by design, which leverages matrix and tensor multiplication, discourages sparse computations. Dropouts is implemented. So if you go and see how dropouts are implemented, and dropouts means you randomly switch off 50% of the node. The way they do it is they will still do matrix multiplication and then add a random mask in front of it, because there is no way of getting out of matrix multiplication, because then the whole advantage is lost. If you take away matrix multiplication, there's nothing left in all these packages, because that's all where the acceleration comes from. You can even write a C++ for loop, will probably be equally fast, of course, with some vectorization. So we cannot identify most cost and energy efficient alternative for a given model. And I think it's a perfect time for innovation, even in the software stack. And we are very excited about working on board and creating a new software stack to actually demonstrate that. With that, here are the acknowledgements. So this is, again, like I am the face, but there are a lot of people who have put a lot of efforts in making this work. And with that, I am happy to take more questions.
Okay, thank you. It sounds very impressive. So one question on chat was, TensorFlow and PyTorch maintainers spend a lot of time compiling thousands of operators into C++ kernels. Do you leverage these, or do you end up writing your own kernels to cover all operators?
So we don't use any of those because, again, these C++ kernels are primarily, again, based on dense computation, right? So because we wrote this, we initially thought that we'll leverage, we don't have to reinvent the wheel, but then we realized that for all our needs, whatever we need is not there. So we have to just build it up. So we wrote everything all our own. So we need hash tables, we have hash functions, we have hash lookups, hash aggregation, and all of those are written. And I don't think there is any library out there that gives you that. So it's a very custom kind of an algorithm, and it required a very custom work.
Well, for different models like YOLO or efficient or vision models, a lot of times they have custom functions in there. So I think they're talking about the different models. As a new paper comes out, a new architecture comes out, sometimes it has a new function. So I think those are the functions they're talking about.
Yeah, and so that's a great question. I'm sorry, I misunderstood that. So the way we work here is, what we realize is we are also not using a lot of standard architectures. We can train really large models very easily. And what we realize is we don't even have to spend time on some sort of a fancy layer to get the best accuracy. So yes, but we have not utilized any of those yet, like C++ kernels.
Okay. Let's see, another question. I may be way off in establishing this correlation, but let me throw it out there for comments. If it makes sense, if it's not a dumb question. If the correlated neurons point to the same bucket, in some ways, we're modeling a Gaussian process around those. If that's the right direction of thinking, are you able to somehow measure uncertainty of your model accuracy? Irrespective of this line of thinking, is there a way to measure uncertainty?
That is a great question. In fact, I would say that one way to think about also is, in fact, one idea that we had in mind is we could actually have as large hidden layer as we please, right? So we typically train models that can have even hundred thousands of hidden layer size, right? Very wide ones. And that is essentially saying that as you throw more data in, you probably need more and more neurons. And again, like this is like some sort of a, what they call as non-parametric Gaussian process kind of a stuff. That's actually a great thought process. And if you can model it, then you can even somehow measure the uncertainty. We have not looked into it, but that is definitely a great idea. Yeah.
Okay. And the same person continues. Also, how does attribution work in this modeling approach? That may be quite critical for recommendation engines.
Yeah, like so from a modeling perspective, we haven't thought much. The way we think about it is it's a very large neural network that you can train with gradient, like gradient descent with sparsity, and so it has all the right ingredient for convergence, minimizing the loss, and that should be sufficient. But yeah, what you are asking about is okay. We can now even think once we start thinking about like the Gaussian process and other. There may be a different way of modeling this. I haven't thought through that much.
Okay, I think in some of our past conversations, there is you had a slide on being able to do model description or model explainability. And when you talk about attribution, is maybe like which source fields are most important.
Yeah. Okay. So I'm sorry, I didn't realize the attribution part. We can totally do that, right? So remember, when we do the forward pass, we do a sparse update, and when we do backward pass, we are still in that sparse network. So our attribution, so we actually in Bolt engine, we have explainability, the root cause analysis module by default. And if when you call that module, it tells you that where the prediction is maximally affected because of these attributes. And in fact, we can also come up and say, well, what if you want the prediction to be something else? Where should the weights and everything go to? And that is actually much easier, and not easier, but it's also more reliable, because even if I have, let's say, thousands of features, because of sparsity or thousands of neurons, it's only attributed to very few. So that's actually a great point. That's one of the things we have, and it works quite well. So great point, Dave. Yeah.
Okay. So let's see. Nitin said, this is very fresh and inspiring. Thanks for sharing. Where can I read more about, one, the LSH algorithms and the theory behind them, and two, the robo array? And maybe a side question is, will you be able to send a PDF of the slides, and I can post them on the meetup? On our meetup for this event, we can have a chat link. Either you can post a link there or send me your PDF slides and I can post the chat link.
I will definitely be able to share I will definitely share the slides, and I can even add an extra slide for references. Thanks. We'll do that for LSH algo, and these are the papers that we have.
Yeah. People generally like to dive into the papers behind things if they get excited. So that would be good if you could share the references. Carl was asking, so this won't suffer from post pruning on model accuracy? I don't think you're doing pruning.
I'm not doing any pruning. Yes. So this is.
I mean, the pruning is happening during the training. The sparseness is happening during training.
Agreed. So thanks, Greg. Again, like I don't want to call it pruning because we are not throwing away anyway. It's just the selection that. So we keep all the parameters, and the algorithm decides what parameter to select and use that for prediction. So there is no pruning.
Yeah. So the LSH is more like a mask of selecting what weights to do calculations over and what activations. But that can change over time during the training process.
Yes.
So I guess that might be, let's see. Okay, just reading. I've struggled with embedding management and memory congestion of DLRM in the past and discarded its use in the process. So they were saying excellent work.
Thank you.
So I think just thanks. Now over in the Q&A, Richard said, so do you stay in a hashed numeric space until the very end? I mean, I think your hash is like a mask, and then what's not being hidden from calculation, you're calculating normally.
Yeah, so we are using so when we decide, like in the algorithm, the hash is used for the selection. Once we select a neuron, we do the exact computation of the activation. But that's a great point. Like if we are likely in a very constrained environment, we could just use the hash space to get an estimate of an activation. Those things can be done. That's a great question.
Okay, sounds good. And continuing on in the Q&A, Lonnie is saying, is there a conceptual connection with dynamic sparsity / hashing and the attention mechanism in transformers?
That's a great question. So attention mechanism in transformers gives weights to pairwise association. Dynamic sparsity is also a selection. Again, like it's you can think of it as a 0-1 kind of a weight, whereas the weight that are selected are ones and the non-selected are 0. But the dynamic sparsity is in the parameter space and attention is in the input space. But I think attention is a very overloaded word. So yeah, there should be some.
Yeah, I mean, in transformers, they have a query, key, and value part of the attention mechanism, and that's part of both the input space and the output space. So if you're going English to French, then you've got the same attention mechanism with the query key value on English, on the current English word, and also on the current French word. Okay, let's see. Warren was asking, what happens to automatic differentiation and backprop with hashing, which is not smooth? Doesn't learning slow because of the discontinuous hashing?
Yeah, actually, that's that is not a problem, because if you think about ReLU is also discontinuous, right? So if you're below 0, it just drops you off. If you're above 0, you get something, right? So hashing is more like, let's say, an adaptive ReLU, right? Where you shut off a node probabilistically, so that does not create a problem. Yeah. So
yeah.
you just backpropagate on whatever is selected.
Right. Mike said, will slides and references be available? And yes, we already brought that up. So good question, Mike. Good to hear from you again. But yes, we'll go ahead and get those slides. Do you want to post a link to the meetup chat, or do you want to send slides to me afterwards?
I'll send the slides afterwards. Yes.
Okay, sounds great. Let's see. Did you have any interest in pursuing vision models, or what was your thought about that for ThirdAI?
Yeah, so I think given the size of ThirdAI, and we are working on so many things, and we got so many interest, I think we decided to actually, unless we expand more, we think that we cannot right now handle vision models. It's for the future. So we started working with vision models recently, but again, like we didn't allocate a lot of resources to that yet. But other than models, we have NLP, we have recommendations, we have forecasting. Then we do a lot of tabular sequential modeling, cold start problems, and all sorts of recommendation problems, and even like recurrence time series kind of a scenario. But yeah,
sounds good. Okay, other questions from the audience? I think I've caught up on the Q&A. Oh yes, the recording will be posted. We'll have a raw YouTube recording in the SF Bay ACM YouTube channel. And then later on, we'll have some edited versions posted later to give an update. So that'll be available for people to watch. Okay, well, let's see. Does your paper have time series results and other areas with the results covered?
Yeah, I think so. Yeah. And, sorry, I missed that part. What?
It just popped up. It says, does your paper, and you have many papers, so but do one of your papers have time series results? So do you work on time series problems? I think.
Yeah. So
they were asking about the kind of domains that you work in.
I think the time series part is in I haven't not written a lot of papers about time series. The time series ones are the white papers that we have from ThirdAI. We can post it soon. Okay.
Oh, somebody was saying thanks, an excellent topic and presentation.
Thank you. Very pleased to hear the feedback.
Sure. Okay. Well, I think we can go ahead and close it down. So I'll give you applause from the audience. And if there's nothing else, then we'll call the meeting done.
Thanks, everyone. Really enjoyed. And again, I can be reached out via email if you have any other questions. Thank you very much.
Excellent. Thank you.
Thank you. Yes.
Thank you, Greg.
Thanks.